We will now look at the second derivative test. From the first derivative test, you know that if a function is increasing, its derivative is positive, and if a function is decreasing, its derivative is negative. Let me write that down for you. I would say if f of x increases, then f prime of x is positive, greater than 0. In the same way, if f of x decreases, the second derivative is, the first derivative, sorry. If f of x decreases, its derivative is negative. Is that right? Now that is what the first derivative test is all about. And also we know from the first derivative test that at a point where f prime x equal to 0, you either have a relative maximum or a relative minimum. Now the first derivative test does not conclusively tell you where you get the maximum or where the minimum. At the point where the first derivative is 0, it could either be a maximum or a minimum. Now the second derivative test will give you more specific information about the maximum and minimum. Now, tell me, if f of x increases, then f prime x, its derivative will be positive. Alright, tell me this. If f prime of x increases, what do you think will be the nature of f double prime x? Now connect this properly. If f of x increases, then its derivative f prime x will be positive. If f prime x increases, how about its derivative f double prime x? Is it reasonable to say that it will be positive? Yes. In an interval where the first derivative increases, the second derivative will be positive. Similarly, on an interval where the first derivative decreases, the second derivative will be, alright, negative. That's right. Now, this is the center of the second derivative test. Alright, let's make it more clear by drawing a diagram. Alright, let's consider the graph of a function. This is the graph of f of x. Now, I have drawn the graph of f of x on the interval x equal to a to x equal to b. Now, on this interval, this is the graph of f of x. I'm going to mark a couple of points on that graph. Let me see if I can get, say, I have a point here, I'm going to call point A. A point here, I'm going to call point B. A point here, I'm going to call C. A point here, I'm going to call D. And maybe a point here I'm going to call E. And what I'm going to do is, I'm going to draw tangent line to the graph at those points. Let's draw tangent lines at x equal to a. Look at the tangent line I'm drawing. At x equal to a, I have a tangent line. X equal to b, I have a tangent line. X equal to C, I have a tangent line. X equal to D, I have a tangent line. X equal to E, I have a tangent line. Now, I want your help here. Now remember, what's the meaning of the first derivative? The derivative of f of x at a given point is the slope of the tangent line. Now, give me an approximate value, well, just a ballpark value of the slope of this tangent line. First of all, tell me, is the slope of this tangent line at A positive or negative? It is negative, is that right? So I'm going to say the slope of the tangent line is about -2. And at B, it's about -1. Well, approximately. And the slope of the tangent line at C is, all right, I thought I heard you saying 0, yes. The slope of the tangent line at D is, say, approximately 1. And the slope at E is approximately 2. Now, when you go from x equal to A to x equal to B, what is happening to the first derivative? It is going from -2 to -1 to 0 to 1 to 2. Tell me, is f prime x increasing or decreasing? Tell me so I can write down here. F prime x here is increasing. That's right. Now, you know from these statements, if f prime x is increasing, how about f double prime of x? F double prime of x is greater than 0. It is positive. That's right. So look at this one more time. If the function graph is given like this, what is the shape of this? Can you give me a name for the shape? Something that opens up. Is it reasonable to call it concave up? See, the concavity of a shape is rather an important property. If you look, if I take this paper and do like this, I'm creating a concavity. This is concave down, and this shape is concave up. So, concave down, concave up. You can see this, the shape of the graph of the function is concave up. And then what can you say about the second derivative of such a function? If the graph of f of x is concave up, then its second derivative will be positive. Why? Because its first derivative will be increasing as x increases. So I'm going to repeat that one more time. Make note of these things. On an interval where the first derivative is increasing, the second derivative will be positive. And on such an interval, the graph of the function will be shaped concave up. Or, rephrase it. If the graph of a function is concave up on a given interval, then the first derivative will be increasing as you go from left to right, and throughout that interval the second derivative will be positive. Okay, one more time, I'm going to rephrase it. If the second derivative is positive on a given interval, what can you then say about the function graph? The function graph will be concave up. Alright, I'm going to draw a graph. Look at this. What is the shape of that graph? It is concave down. And let me mark some points on that graph. Alright, I'm going to mark a point here, A, a point here, B, a point here, C, a point here, D, and a point there, E. Now tell me, if I draw the tangent lines at these points, I'm drawing a tangent line at x equal to A tangent line at x equal to B, a tangent line at x equal to c, a tangent line at x equal to d, and a tangent line at x equal to e. Now, I want you to give me approximate values of the slopes of these tangent lines. If you notice, the slope of this line is positive, that is positive, well, that is negative, that is negative. Give me an approximate value here. Well, let's say positive 2. And if you look at that, the slope of that will be less because it is getting flatter. So let's say the slope there is 1. And the slope there is 0. Is that right? And if the slope at D is negative 1 and at E it is negative 2, now what you notice is that as you go from x equal to A to x equal to B, on that interval, the first derivative is, can you complete my statement? The first derivative is decreasing. If the first derivative is decreasing, how about the second derivative? It will be negative. So on such a case, the second derivative is negative, is less than 0. And therefore, is it reasonable for us to say this? On an interval where the function graph is concave down, the second derivative will be negative. Why? Because the first derivative will be decreasing, isn't it? From 2 to 1 to 0 to negative 1 to negative 2. Now, put that in another way. If the second derivative is negative on an interval, then the graph of the function will be concave down on that interval. Alright, I want you to sort of re-watch this one more time and learn this property. Here we are actually summarizing both the first and second derivative tests. Alright, look at the graph of this function. This is the graph of f of x. Can you talk about this? Now, I have marked the x values, a, b, c, d, e. Alright, tell me, what is the behavior of the graph of this function from x equal to a to x equal to c? From x equal to a to x equal to c, the graph of the function is concave up. So I can say on the interval AB, this is the way we write normally the open interval. On the open interval AB, the graph of f of x is concave up. Now, therefore, we are sure about one thing. What are we sure of? We are sure about this. Its second derivative, therefore, is positive or negative, where the graph is concave up. It will be positive, greater than 0. Yes. Alright, how about at x equal to b? You know that at x equal to b, the tangent line is horizontal. The first derivative f prime x equal to 0. Alright, let's look at the behavior from x equal to c to x equal to e. On the open interval, so I'm going to write it over here. On the open interval, say CE, the graph of the function is concave down. Is that right? The graph of the function is concave down. Now, if the graph of the function is concave down from our discussion on the second derivative test, how about the sign of the second derivative? F double prime x will be less than 0 or negative. Now, how about the value, how about the behavior at x equal to d? At x equal to d, your first derivative is 0, isn't it? All right. Now, according to the first derivative test, if f prime x is 0, you can either have a maximum or a minimum. Now, can you combine the first and second derivative test and form a definite conclusion about where we get the maximum and where we get the minimum? Where do we get a relative maximum? A relative maximum occurs at what kind of a point? We get a relative maximum at a point where the first derivative is 0. Now this is a point of relative maximum, is that right? At that point, the first derivative is 0 and the second derivative is negative. Is that right? The second derivative is negative. Now, this is the condition for a relative maximum. Very important to know that. So, at a relative maximum, the first derivative is 0 and the second derivative is negative. How about a relative minimum? We have a relative minimum at x equal to b. A relative minimum at x equal to b. And you know at x equal to b, the first derivative is 0. And how about the second derivative? If you notice, the second derivative is positive all along the interval from a to c. So at x equal to b, the second derivative is positive. That means, if I ask you what is the condition for a relative minimum, both these need to be satisfied to get a relative minimum. The first derivative must be 0 and the second derivative must be positive. Now look at that. The two tests, the first derivative test and the second derivative test combined, gives you some definiteness about where exactly a relative maximum occurs and where a relative minimum occurs. Okay, I want to ask you about this point on the graph. At x equal to c, if you notice, on the interval from a to c, the graph of f of x is concave up, isn't it? And from x equal to c to x equal to e, the graph of the function is concave down. That means, how about at x equal to c? At x equal to c, you change from concave up to concave down. So c is the point of transition. Alright, in that case, what can you tell me the value of the second derivative? What can you say about the value of f double prime x at x equal to c? Well, you can see from x equal to a to x equal to c, all along here, the second derivative is positive. And from x equal to c to x equal to e, it is negative. Now look at this. When you talk about the interval, we are talking about open intervals. In other words, the endpoints are not included. C is not included in that interval. Now what is the value of f double prime x at x equal to c? From x equal to a to c, you have second derivative is positive. And the only way you can transition from a positive to negative is to go through 0. Is that right? If you look at the number line there, you say this is positive 3, positive 2, positive 1, 0, negative 1, negative 2. So you can see the second derivative is positive and the positive values give way to negative. The only way that can happen is to go through 0. That means at x equal to c, the second derivative is 0. That is where the concavity changes from concave up to concave down. And such a point is called a point of inflection. Inflection. So a point of inflection is the point where the second derivative is 0. There you go. Now, we have now enough information using the first derivative test and the second derivative test. You can now use them to plot the graph of a function in a much more accurate way, because we now know the concavity, whether the graph is concave up or concave down on a given interval. Let's take a look at this function graph, and this actually illustrates what happens when x increases from left to right. I can actually drag this to increase the value of x, and a tangent line drawn at the point measures the slope, and the slope value is given here. So watch as I move to the right. What happens to the slope? The slope is becoming less and less. Is that right? The positive slope is becoming less, and the slope becomes 0, and now the slope becomes negative. It's become more and more negative. That means the first derivative is decreasing. Alright, as you go to the right, it becomes 0 again, and then increases. And what you have here is from x equal to this point to about here, the graph is concave down. You saw the first derivative was decreasing, isn't it? I just showed you. The first derivative was decreasing. That means the second derivative is negative. The second derivative is negative, means the graph is concave down. And look here, what happens to the first derivative there is negative 0.7, negative, say, 0.62. It is increasing, it's become 0, and it is increasing. So on this interval, the first derivative is increasing, means the second derivative is positive, the graph is concave up. And somewhere here, the concave down gives way to concave up, and that is where you have the point of inflection. Alright, well, that illustrates it a little better than the ones I drew. Let's now summarize what we have already said. Now, at a point where a relative maximum occurs, what are the conditions to satisfy? You've got to have f prime x has to be 0 and f prime x has to be negative. On a relative maximum, the first derivative is 0 and the second derivative is negative. At a point where a relative minimum occurs, the first derivative is 0 and the second derivative is positive. So now we know exactly where we can get a maximum or a minimum. And also a point where the second derivative is 0, where the concavity changes, you got a point of inflection. And if if the second derivative is positive, the graph is concave up. If the second derivative is negative, the graph is concave down. That is a summary of what we already did. Alright, let's use this now to do a couple of problems. Now, the first antiderivative test we are going to use to plot the graph of a function. All right. Find all relative extrema and the point of inflection and graph the function of f of x equal to x cubed times x minus 4. Find all relative extrema. Now, that is what we did in the last lesson. In other words, we need to find the critical numbers. So, in here, we need to find the critical numbers, and once we find the critical numbers, what do? Divide the domain of the function into certain number of intervals and find the behavior of the function on each interval, depending on whether the first derivative is positive or negative. Then we obtain the points of inflection, points where the second derivative is 0. And again we do the same thing. We divide the domain of the function into certain intervals and determine whether the graph of the function is concave up or concave down, depending on whether the second derivative is positive or negative. Now, these are the things that we are going to do. Therefore, we start by doing first the critical numbers. We obtain the critical numbers by setting the first derivative to 0. This is our f of x. F of x is x cubed times x minus 4. Can you find the first derivative quickly? Now remember, you can do it in either way. You can distribute it and use the power rule, or you can use the product rule. The first function times the derivative of the second function plus the second function times the derivative of the first function. So this is f of x equal to x cubed times x minus 4, and let's do it by expanding it. That is x to the power of 4 minus 4x cubed. It's much easier now to find the derivative. Is that right? All right. What's the derivative then? F prime x is the derivative of x to the power of 4 is 4x cubed minus derivative of 4x cubed is 12x squared. And set this equal to 0. 4x cubed minus 12x squared equal to 0. Can you solve that quickly? Give me the values of x that will make this 0. Well, first of all, you can factor out a 4x. So that will 4x squared. That will be 4x squared times x minus 3 equal to 0. Now, when 4x squared becomes 0, x equal to 0. So x equal to 0 is one critical number. And when x minus 3 equal to 0, you get x equal to 3. And that is the other critical number. So what are our critical numbers? X equal to 0 and x equal to 3 are the critical numbers. Alright, now we have the critical number. We're going to divide the domain of the function. Well, the domain of this function is from negative infinity to positive infinity. Now, if these two are the critical numbers, how many intervals are there? There are 3 intervals. What are they? The first interval is from negative infinity to 0. The second interval is from 0 to 3. And the third interval is from 3 to infinity. Now, once we have those intervals, we will pick test numbers and use the test numbers in the first derivative to see if the first derivative is positive or negative on that given interval. Well, if the first derivative is positive, are you listening to me carefully? If the first derivative is positive, how about the behavior of the function? The function will be increasing. If the first derivative is negative, the function graph will be decreasing. That's what we want to find. Alright, let's go and do that. Now, the intervals in the domain of f of x are, what are the intervals? Negative infinity to 0, that is one interval, 0 to 3, and 3 to infinity. Those are the three intervals that these two critical numbers give you. Now, what's the next step? We take our test numbers. All right, give me a test number from negative infinity to 0. The test number, well, it's very simple. Pick one, negative 1. You can pick any number, it doesn't matter. But it must belong to that open interval. Give me a number from that open interval, 0 to 3. Well, 2 or 1. From 3 to 1, 4 is a good number. Now, what we now want to do is find the sign of the first derivative. Remember, we are not interested in the value of the first derivative. We want to know if the first derivative is positive or negative in that interval. So if this is the function, we need to find the sign of the first derivative at these test numbers. How do we do that? Let's go to our calculator. Do you remember how to do that? Alright, let's use the calculator to find the sign of the first derivative of this function at these test numbers. Alright, to begin with, we need to turn on the calculator, which I very often forget. So turn on the calculator and maybe clear whatever we don't want. And where do we go? Well, clear that screen. Now press y equal to and enter our function. Clear that first. Clear y1. y1 is x cubed times x minus 4. So we say x to the power of 3 times x minus 4. That will be that. Okay. That's our function. F of x equal to x cubed times x minus 4. And as I have shown you before, y2 is the derivative of y1. Is that right? Well, if you have forgotten how to enter y2, let's start it all over again. Let's clear that. And what do we enter? y2 is the first derivative of y1. So first go to math. Where do you find math? Math. And number 8 is the first derivative. So press 8. That prints derivative of what? We need to find derivative of y1. Where do we get y1? Go press on vars, V-A-R-S, and go to the right, pick y vars, and you can see what is highlighted is function, and that's what we want. So enter, and y1 is highlighted, so if you enter, that will be picked. Alright, we got nth derivative of y1. Now a comma. Now here's a comma. Comma with respect to x, and for some reason this calculator requires another x there. I don't know why. It should have been just y1 with respect to x, but it needs to, so give it to. Now that means this is the way we write it. Nth derivative of y1 with respect to x for x and close the parenthesis. That's our y2. Now, because we are using the second derivative test, we are going to have y3. y3 is going to be the second derivative of our function, which is, remember, the second derivative of the function is the derivative of the first derivative, or it is the derivative of y2. So what we're going to enter here is the derivative of y2. Now, can you do that on your own? Go to math and pick number 8. Now, we want the derivative of y2 now. All right, how do we pick that? Go to vars, to the right to pick y vars, and function. We now need y2, so go down and pick y2 and enter. It is now the derivative of y2 comma x parenthesis closed. And now we are ready. Now I want you to do one more thing. Finally, we will be graphing it, and we don't want our graph to be muddled up with the graph of y2 and y1. So go take the cursor to the equal sign of y2 and y3, something like this. Now, you see the cursor is now sitting on the equal sign of y3. Enter there, and you see that is deselected. Similarly, enter on y2 and deselect it. And now when you graph it, only y1 will be graphed. But these expressions will help you to find the values of the first derivative and the values of the second derivative when you need them. All right? Okay, so do that on the... Now, we need to find the values of the first derivative at x equal to -1, x equal to 1, and x equal to 4. So let's go back to the calculator and do those first, so that we know the sign of the first derivative on those test numbers. All right? Let's do that. We are now doing the first derivative test. That means we need to find the value of the first derivative. First derivative is y2, is that right? So let's quit this and go and pick y2. Vars, right arrow, enter, down arrow once, y2. y2 is our first derivative. We want the value of the first derivative at x equal to -1. So put a parenthesis. Where's the parenthesis there? The parenthesis -1. Is that right? Parenthesis -1 and parenthesis closed. What do you get? Well, we are not interested in the number. We are interested in the sign. It tells you that the first derivative is negative on that interval. And I showed you, you don't have to go back to find this y2. Press second enter, and you got that y -1 there. Now go back there and change that to y of 1. Just delete button there and enter, and that again is negative. So the first derivative is negative from negative infinity to 0, and also from 0 to 3. All right, let's get the value of the first derivative at x equal to 4. What do? Second enter, and go back there and change that to a 4. There you go. And enter. That is positive. So take note of that. The first derivative at x equal to -1 is negative. At x equal to 1 it is negative. At x equal to 4 it is positive. Okay. So we now know that on the interval negative infinity to 0, the first derivative is negative. Is that right? I hope you took note of that. And, well, I give you the calculation here. You don't need the calculation. And on the interval from 0 to 3, again it is negative. I gave you that calculation there. And on the interval 3 to infinity, the first derivative is positive. And therefore, now, what is the conclusion therefore? Now, what is the behavior of, therefore, the first derivative? The first derivative is negative, means the function is decreasing. So f of x is decreasing on this interval. How about here? Again decreasing. How about here? It's increasing. Now, that's funny, isn't it? You have a critical number. Now, according to our understanding, a critical number must either give you a maximum or a minimum. But if you look here, on the left of the critical number, the function is decreasing. On the right also it is decreasing. Can you get a maximum or a minimum there? Well, so f of 0, the function value at that critical number, is neither a maximum nor a minimum. Now, how does that fit into our discussion? Can you think of a graph that decreases on the left and decreases on the right of a critical number where the derivative is 0? Well, that's not very difficult. If you just let me put this screen up, I will just show you. Well, that's pretty messy. Well, what it tells you is that on one interval it is decreasing, and on another interval also it is decreasing. Look at that. In between you have a place where the derivative is 0. That's how it comes. So you have decreasing on the left of x equals 0, decreasing on the right of 0. But you can see here the concavity is changing. You see the concavity is changing. If it is concave up on the left, it's concave down on the right. And in between you have a point where the derivative is 0. So that is possible for a graph. That means at all critical numbers you may not get a maximum or a minimum. So f of 0 is neither a maximum nor a minimum. But how about x equal to 3 is a critical number, and on the left of 3 it is decreasing, on the right of 3 it is increasing. That means if you have to decrease and then increase, at x equal to 3 you have a minimum. And if you now put x equal to 3 on the function there, f of 3 is negative 27. Try that on your calculator. Find the value of the function when x equal to 3. That will be negative 27, and that is a relative minimum. Well, we have done with the first derivative test. Let's now use the second derivative test to see on what interval is the function concave up and on what interval is it concave down. And we do that by finding the second derivative and set it equal to 0 to find the point of inflection, points of inflection. Well, you notice from our discussion earlier, the first derivative is 4x cubed minus 12x squared. Is that right? Yes. Now, if you find the derivative of this, you get the second derivative. So what is that? The second derivative is 12x squared minus 24x. And set this equal to 0 to get your points of inflection. And can you solve this? 12x squared minus 24x equal to 0. Factor out at 12x, and that is 12x times x minus 2 equal to 0. And that will be very easy to understand. X equal to 0 is an inflection point. Remember, this is the second derivative. At points where the second derivative is 0 are called inflection points. Inflection points are points where the concavity changes. X equal to 0 is an inflection point. X equal to 2 is the next inflection point. Now, we can now divide the interval of the domain of the function into 3 intervals to find where exactly do we have concave up and where do we get concave down. Now, 0, 0 and 2, negative 16, when x equal to 2, y equal to negative 16. Remember, we are always dealing with the function. Now, these inflection points divide the domain of the function into 3 intervals. What are they? It will be negative infinity to 0, 0 to 2, and 2 to infinity. What we will do again, we will choose test numbers. Remember, we are doing the second derivative test. We choose the test numbers and use those test numbers on the second derivative to see if the second derivative is positive or negative. If the second derivative is positive, then the function graph is concave up. If the second derivative is negative, then the function graph is concave down. So to determine the concavity, we use test numbers on these intervals, on the 3 intervals, on the second derivative. Alright, let's do that. These 3 intervals are negative infinity to 0, 0 to 2, and 2 to infinity. Give me test numbers there. Negative 0, negative infinity to 0, you can take negative 1. 0 to 2, the test number is 1. And 2 to infinity, the test number is 4. And these test numbers are for the second derivative. That means you've got to go to the calculator and find y3. y3 of negative 1, y3 of 1, and y3 of 4. Because we have entered in our calculator y1 is our function, y2 is the first derivative, y3 is the second derivative. Alright? So do that on your own, or do you want me to do that one more time for you? That's very simple. Go and calculate y3. Well, alright, let's get y3 on the screen. How do you get that? Go to vars. Turn on the calculator, sir. Go to vars. Right arrow to function. Now choose y3. Go down and choose y3. Enter. y3 of negative 1. So y3 of negative 1 is positive. We don't need the value. It's positive. How about y3 of 1? Well, second, enter, and change it to y3 of 1. Just delete that negative. Well, that is negative. So you can see the second derivative is positive in the first interval, negative in the second interval. All right. Go and try that one more time. Change that 1 to a 4, and there you have positive. Alright, let's do that on the board. So we found the second derivative is positive on this interval, negative on this interval. Don't worry about the calculation, I just gave it to you. Since you're using the calculator, that's not relevant. And on this interval from 2 to infinity, it is positive. Now, if the second derivative is positive, what can you say about the graph of the function? The graph of the function is concave up. So the graph of the function is concave up. The graph of the function is concave down, where the second derivative is negative. And the graph of the function is concave up, where it is positive. We have now lots of information about the graph of that function. We know the interval where the function is increasing. We know where the intervals where it's decreasing. We know the interval where the function graph is concave up. and the interval where the function graph is concave down. We put it all together. Now look, you've got to keep all this information, assemble all it, and then draw the graph of the function. Now look at all the information I have here. I have negative infinity to 0, 0 to 3, 3 to infinity. These are the three intervals using the critical numbers. And then using the second derivative, the inflection points, we have the intervals negative infinity to 0, 0 to 2, and 2 to infinity. And if you go back, we had done this already. We know on negative infinity to 0 the function is decreasing. 0 to 3 the function is decreasing. I showed you how that can happen. And 3 to infinity it is decreasing. But from negative infinity to 0 it is concave up. And 0 to 2 it is concave down. And from 2 to infinity it is concave up. Can you use this information to plot the graph? Let's do that. Alright. It says f of 3. First of all, you know that at 0 to 3 the function is decreasing, and 3 to infinity it is increasing. So decreases and then increases means at x equal to 3 you have a relative minimum. Is that right? Find that first. F of 3 equal to negative 27 is a relative minimum. And there you got 3, negative 27. And then on negative infinity to 0, f of x is decreasing. Look at this. You've got to combine this. At negative infinity to 0, the function is decreasing and concave up. Look at the graph. It's decreasing and concave up. Then on 0 to 3 it decreases, but on 3 to infinity, well, 0 to 3 f of x is decreasing. From 0 to 3 it is decreasing, and from 0 to 3 it is, well, 0 to 2 it is concave down, and thereupon it is concave up. So on 0 to 3 f of x is decreasing, and from 3 to infinity it is increasing. So from here to here you got a graph that is decreasing, and from here onwards you have a graph that is increasing. But on 0 to 2 the graph is concave down. So when you have a graph that is decreasing and concave down up to x equal to 2, and from 2 onwards it is concave up. But from 2 to 3 it is decreasing, and then it is increasing. Look at that again. From 0 to 3 the graph is decreasing, but from 0 to 2 it is concave down, and from 2 onwards it is concave up. And look at how beautifully we are able to draw the graph of this function. Isn't that good? Alright, I want you to practice this more number of times. So where is the inflection point? That is one inflection point where the concavity changes from concave up to concave down. And another one is over here at x equal to 2, where it is concave down and changes to concave up. Alright, now I want you to do this. Use all these instruments that we developed and plot the graph of the function f of x equal to x cubed minus 9x squared plus 27x. Now remember, don't go away, just sit there and do this before you go to the next part of the video. Alright? Okay, let's, I've given you the answers, so let's try now this one. Find all relative extrema and the points of inflection and graph the function f of x equal to sine x plus cos x on the interval 0 to 2 pi. Now if you remember in the last lesson we did f of x equal to sine x times cos x. This time we have sine x plus cos x. Alright, let's get along with it. Let's work on it on the board. I'll go back to the PowerPoint when it becomes a little too cumbersome for me to fit on the board. Alright, our function is f of x plus cos x, and we need to find the graph of this, the behavior of this, on the interval 0 to 2 pi. Okay, what's the first step? Find the derivative of this, set it equal to 0, and find the critical numbers. That's our first step. Okay, let's start here. What is the derivative? F prime x equal to sine x. The derivative of sine x is cos x. The derivative of cos x is negative sine x. So it's cos x minus sine x. And set it equal to 0 and solve for x on the interval 0 to 2 pi. We are not interested anywhere else. Can you solve that equation? Cos x minus sine x equal to 0. This is actually much simpler than the one we did in the previous class. What do we do to solve such an equation? Remember, any trigonometric equation can be solved only if you get rid of the 2 ratio equation and reduce it into a 1 ratio equation. Is it possible to get rid of the 2 ratios and replace it by a single ratio? Well, to do that, you need to have an understanding of the trigonometric equations and identities. You should know that sine x divided by cos x is tan x. And so, on this equation, if you divide each term by cos x, let's do that. Divide this by cos x, divide the next one by cos x, and divide the right side also by cos x. Cos x divided by cos x is 1 minus sine x divided by cos x is tan x, and 0 divided by cos x is 0, and that gives you tan x equal to 1. Alright, when does tan x become 1? Tan of what number is 1? Remember, I told you, always think in degrees and then convert it to radians. Now, in this part of calculus, we don't use degrees, we always use radians because they are real numbers. Tan of 45 degrees is 1. 45 degrees is pi by 4. Now, that gives you x equal to pi by 4. But there is a small problem. Now, look at this. From 0 to 2 pi, 0, pi by 2, pi, 3 pi by 2, 2 pi. I showed this to you in the last class. 0, pi by 2, pi, 3 pi by 2, and then back to 2 pi. Now, where is our pi by 4 as the radius vector rotates? This is pi by 4. Well, tangent of pi by 4 is 1. But tangent is positive in the first quadrant and also in the third quadrant. Do you remember that? Well, sine is positive in the first and second quadrant. Cosine is positive in the first and fourth quadrant. I hope you know that. Tangent is positive in the first and third quadrant. That means tan x equal to 1 can happen in the first quadrant, also in the second quadrant. So x equal to pi by 4 is the value in the first quadrant. You also get a value in the third quadrant, which is this value. Look at this. How much is that? You must go like this. This is 1 pi by 4. This is 2 pi by 4. 2 pi by 4 is pi by 2. And this is 3 pi by 4. This is 4 pi by 4, which is pi. And this will be, therefore, 5 pi by 4. And therefore, tan x equal to 1 will give you two values of x. One x is x equal to pi by 4. And the other is 5 pi by 4. Alright, that means our critical numbers are x equal to pi by 4 and 5 pi by 4. I hope you understood the way I explained this, why we have two values for x, for tan x equal to 1. Tan x equal to 1 can happen in the first quadrant and also in the third quadrant, because tangent is positive in the first and third quadrant. So the critical numbers of this function is that x equal to pi by 4 and x equal to 5 pi by 4, and this will divide the domain, the given domain 0 to 2 pi, into three intervals. And what are those three intervals? The intervals are, let's say, 0 to pi by 4, that is first interval, pi by 4 to 5 pi by 4, and 5 pi by 4 to 2 pi. Those are the intervals. Okay, we now need to obtain test numbers. Test numbers on this interval. Alright, give me a test number from 0 to pi by 4. Now, to do that, again, draw that diagram. Now, this is 45 degrees, that is pi by 4. Now, you can take as test number anything between 0 and pi by 4. Give me a number between 0 and pi by 4. Well, pi by 6 is a number between 0 and pi by 4. So I'm going to choose pi by 6 as a test number. And the interval from, this is pi by 4, and this is 5 pi by 4. Well, on this interval, give me a test number. There are many good test numbers there. There's a pi by 2 that is in that interval. There's a pi also in that interval. So take any of those. Let's take pi by 2. And the interval from 5 pi by 4 to 2 pi, a good test number there is this. What is that? 3 pi by 2. 3 pi by 2. So let me take that away. Always use these kind of diagrams to get your test numbers. Very important. And now, once you have your test number, you need to get the sign of the first derivative. Now, is the first derivative positive or negative on this? Well, do that on your own. Use your calculator and try this on your own. Or maybe I will do this also for you quickly. Well, I decided to let you do that on your own, and I'm continuing here to save a little time because this lesson has gone over an hour already. Well, on 0 to pi by 4, the first derivative is positive, therefore the function is increasing. On pi by 4 to 5 pi by 4, the second derivative is negative, therefore the function is decreasing. And on 5 pi by 4 to 2 pi, the first derivative is positive, therefore the function is increasing. And now, if you look at the left and right of pi by 4, on the left of pi by 4 the function is increasing, on the right it is decreasing, therefore you have a relative maximum. And you can find the relative maximum by putting x equal to pi by 4 in the function sine x plus cos x. And that will give you sine of pi by 4 plus cos of pi by 4 is 1.41, is a relative maximum. Try that on your own. Similarly, what is the function at x equal to 5 pi by 4? It is negative 1.41, and that is a relative minimum. So we have identified a relative maximum and a relative minimum. And now we've got to figure out where is the function graph concave up and concave down using the second derivative test. Let's do that. Now, you know the first derivative we already did is cos x minus sine x. Now, therefore, the second derivative is, the derivative of cos x is negative sine x. The derivative of sine x is cos x. Therefore, the second derivative is negative sine x minus cos x. Now, set that equal to 0. Negative sine x minus cos x equal to 0, and solve it for x. You can use the same method. Divide each term by cos x, is that right? Divide each term by negative cos x so that the negative terms will go. By doing that, you get tan x plus 1 equal to 0. And that gives you tan x equal to negative 1. And tan x equal to negative 1 will give you, what are the values of x? Remember, tan x is positive in the first and the third quadrant. It means it will be negative in the second and fourth quadrant. And if you go systematically what I gave you, in the first quadrant is pi by 4, then 2 pi by 4, then 3 pi by 4 in the second quadrant, 4 pi by 4, 5 pi by 4 in the third quadrant, 6 pi by 4 is the same as 3 pi by 2, and 7 pi by 4 in the fourth quadrant. So tan x equal to negative 1 will give you x equal to 3 pi by 4 in the second quadrant and 7 pi by 4 in the fourth quadrant. So x equal to 3 pi by 4 in the second quadrant and x equal to 7 pi by 4 in the fourth quadrant. Draw that diagram and figure it out on your own. Now, these are therefore the inflection points. X equal to 3 pi by 4 and x equal to 7 pi by 4 are the inflection points. And we can now construct how many intervals? 3 intervals. 0 to 3 pi by 4, then 3 pi by 4 to 7 pi by 4, and 7 pi by 4 to 2 pi. These are the intervals where we can determine if the graph is concave up or concave down. Alright, give me test numbers on this. Give me a test number from 0 to 3 pi by 4. Pi by 2 is a good one. Again, keep that diagram with you. 3 pi by 4 to 7 pi by 4, there are very good test numbers. Pi is a good one there. And 7 pi by 4 to 2 pi. 7 pi by 4 to 2 pi. Well, a good one is 11 pi by 6. We took that yesterday also. 11 pi by 6 is 330 degrees. Alright, we now find the sign of the second derivative at these test numbers. What all we need to do is find f double prime of pi by 2, replace x by pi by 2. Use the calculator or just do it by replacing x by pi by 2. You will get, if you replace x by pi by 2, you will get the answer negative 1, which is negative. So the second derivative is negative on this interval. It is positive on this interval. And Is it positive? No, it is negative. So you must correct this to less than 0. So from 0 to 3 pi by 4, the second derivative is negative. From 3 pi by 4 to 7 pi by 4, the second derivative is positive. And from 7 pi by 4 to 2 pi, the second derivative is negative. It should be negative, not positive. Well, if the second derivative is negative, what can you say about the concavity of this? Concave down. Second derivative negative, concave down. Second derivative positive, concave up. Second derivative negative, concave down. Now, you know the intervals where the function is increasing and decreasing. The intervals where the function graph is concave up and concave down. Combine all these and plot the graph of the function. Let's do that. I have put down all these values in there. Critical values are x equal to pi by 4 and x equal to 5 pi by 4. Now, use your calculator to find the function values there. The function values. F of pi by 4, in other words, f of x equal to sine x plus cos x. Once you have it entered in your calculator, find y1 when x equal to pi by 4 and x equal to 5 pi by 4. That will give you the function values at these critical numbers. They could be either maximum or minimum, is that right? Then you know that the function increases from 0 to pi by 4 and also increases from 5 pi by 4 to 2 pi. The function decreases from pi by 4 to 5 pi by 4. Then you also know that the function graph is concave down from 0 to 3 pi by 4 and also from 7 pi by 4 to 2 pi. Picture all this in your mind. It is concave up on 3 pi by 4 to 7 pi by 4. Alright, let's put all this together and draw the graph of the function. Now, use your calculator and make sure that your y1 is changed to sine x plus cos x. That's the only change you need to make on the calculator. And find the value of y1 when x equal to pi by 4 and see whether you get 1.41. So when x equal to pi by 4, the function value is 1.41. It is a relative maximum. Similarly, find the function value y1 when x equal to 5 pi by 4, and that is 5 pi by 4 negative 1.41. That is a relative minimum. So you have the relative maximum, relative minimum. Then you have the function is increasing from 0 to pi by 4, also increases from 5 pi by 4 to 2 pi. You can see it's increasing here and increasing here, and in between it decreases on pi by 4 to 5 pi by 4. From here to here it is decreasing. So look at that. Increases on here and increases there and decreases here. But that doesn't really give you a picture. You need to look at the concavity. It's concave down from 0 to 3 pi by 4. Look at that, 0 to 3 pi by 4. Concave down, that means it must come like this. So 0 to pi by 4 increases and concave down. Alright, then there you go. 0 to pi by 4 increases and concave down. Pi by 4 to negative pi by 4 to 3 pi by 4 increases and decreases and concave down. Watch that one once again. From pi by 4 to 0 to pi by 4 increases and concave down. Then pi by 4 to 3 pi by 4 decreases and concave down. Alright, how about 3 pi by 4 to 5 pi by 4? If you look at this, 3 pi by 4 to 5 pi by 4, you know the function is decreasing and it is concave up. So, from 3 pi by 4 to 5 pi by 4, the function decreases and concave up. Look at that. And from 5 pi by 4 to 2 pi, it is increasing and concave up. On this interval, it increases and concave up. And look at that beautiful function graph we have constructed. Well, I want you to spend some time with this, and I know it is a little tough, but spend time with it and you will master the art of doing this. So, I want you to now go back and do one on your own. And you can see 7 pi by 4 to 2 pi is increasing and concave down. Right. Now, inflection point, the concavity from concave down to concave up. That's an inflection point. And this is another inflection point. Concave up to concave down. Alright. Now look at the graph of that. You can plot that graph on your calculator on your own. And now try doing this. Find all relative extrema and the point of inflection and graph the function f of x equal to x minus sine x on 0 to 2 pi. It's a little simpler than you think it is. So try that and let me know how it is going. And don't forget to communicate with me when you have trouble, alright? This is a rather difficult kind of concept, so probably you need help. And anytime you need help, let me know and I will answer all your questions.